Hello everyone, this is Hongik and Junyang's Advanced Machine Learning Project presentation. The structure of our presentation is as follows. We will first introduce the theme of our topic, next design/implementation, then training, and finally the result. The prediction of how the weather will change even the next day is challenging. The experts working at KMS make mistakes all the time. So we try to predict if it will rain, at least in the next hour, given the current meteorological information. We hate rain, and in hopes of correctly predicting the chance of raining, No Rain Please is the title of the project. Our environment setup is as follows, and the data is gathered from official KMS website. We chose seemingly relevant features such as humidity, amount of cloud, etc. Here is the quick overview of the data. We trained the last 10 years of data in Seoul and tested against Jeju's data for validity. We tweaked the features as the difference of value range between features is too large. For example, the atmospheric pressure usually sits at around 1000. However, other values like temperature just won't go to that extreme value. We went to normalize the features because if we train these features as is, it will result in large loss value, thus creating stronger bonds to those features. Since we are trying to predict if it will rain in the next hour, given the current information, offsetting the feature and target array is paramount. Then we fed the data to corresponding output value, which is the next hour's result. Like so, and it is a classification problem because the output can only be either 1 rain and 0 no rain. Here is how the implementation is designed. Models are laid out using Keras sequential module. First layer input 8 units, since the number of dimensions should match the features we chose. The training takes steps, outputting smaller and smaller in size, until we get one final answer. At the end of each layer, there is ReLU activation function. This is widely known technique used to introduce non-linearity to the model. However, we are using sigmoid at last layer as we are only classifying in two classes, rain or not. For such binary classification, it's well known that combination of sigmoid output combined with binary cross entropy works on par or slightly better than using a softmax. Lastly, we use Atom Optimizer because, as you know, it just works. While we do not want files piling up in Google Drive, but wasn't diligent enough to clean it regularly, one trick we did was to modularize our datasets and cloning into session via Git. First, we process our dataset and then push those into GitHub repository. This way, we can easily import our pre-processed data just with the simple git clone command in the Colab notebook file. Then Colab will clone the repository and import the dataset module we created. No more manual upload on every new session or piling up in Google Drive. As for training, we had to find new learning rate due to the Adams default learning rate of 0.001, overfitting our model just after first epoch. Instead, we found that learning rate of 10 to the power of -5 produced more promising graphs. And here's the accuracy and loss graph for our model with new learning rate. This shows dramatic increase in accuracy while not developing overfitting tendency. We have to though confirm that our model actually works, that is, given the current data, predicting the likelihood of raining in the next hour. As shown in the slide, the model could not predict the likelihood of raining. However, it could very well predict that it will not rain in the next hour at about 90 to 95% accuracy. To improve accuracy, we added additional layer to our model, only to find out less desirable result. The case of recurrent neural network, training took 30 times more time to train, while not attributing to any substantial improvement in the accuracy. One possible reason for low accuracy of raining could be that the number of hours that rained compared to not rained is a mere fraction. Our model likely did not learn as we wanted due to the unbalance of the output data. Additionally, there was few errors with dramatic value difference as shown on the graph. And this data is already zero-fitted and normalized. Such outstanding errors could have adversely affected the training. From the failure, we learned that the complexity of model did not impact the outcome significantly. Rather, it was the quality of the data that mattered the most. However, we also was quick to learn that finding such quality data is quite tricky. Good data just doesn't fall from the sky. We have to be the ones who make it happen. This is it. Thank you for watching.